1 week where I can chill. And then I'll have 1 week at the end of the semester where I can chill. So I'll have to study for finals. But I can start studying for finals early in the new month. If you know, you can survive.
Okay, good morning everyone. Few announcements before we get into our exploration of one-dimensional kinematics. Let's see how this is. Okay. Alright, so these are up on the right hand of the chalkboard. Mastering physics. I've been monitoring as you guys have been gaining access, starting to work. By and large, looks okay. I had one person just ask me about a small issue of trying to find where the ebook is, but broadly speaking, any issues, questions about mastering physics? Yes, sir.
My books are backward right now, so
Your book?
my textbook is on backward.
Okay.
So I don't really know when I'm going to be able to get the access code to get on mastering physics.
Okay. I've had a couple of you also indicate delays in getting access. If you haven't contacted me about that and this impacts you in some way, send me a quick email just so I know who's having issues getting access, and I will make a decision on how to handle that in the next 24 hours. Other things with mastering physics. So most of you have done the introductory exercise. If you haven't yet done so, I strongly recommend you do. It's really helpful just to figure out how the whole system works and some of its quirks, because of course there's a real problem set to do in 2.5 days. Yes? So the question was, if you're graphing a curve in mastering of physics, is there another way to do it other than okay, other than graphing a point every whatever it is rotation on the axis? My answer is I don't know. Not very helpful, obviously, but by and large, you won't generally have problems that involve graphing for precisely these reasons. It's obviously a subtle thing to get this to work in something like mastering physics. If anyone knows the answer to that and feels free to upload it to Piazza within coursework, please do so. Okay? And let me encourage you again, a fair number of you are signing up for Piazza. If you haven't, why not? It's in principle a good forum for transmitting information between all of you and to some extent between me and all of you. Hasn't been used much so far, but it could be a pretty useful tool, so I encourage you to try that out. Other mastering physics issues. Okay, good. So, second item, recitations begin this week, today and tomorrow. Most of you have signed up. There are a few of you again who have some maybe scheduling issues. If that's the case, come and see me after class today. It seems to have been settling reasonably well, but I know some of you are still having difficulty. If that applies to you, come and see me after class. Let me just tell you what I'm hoping will happen in recitation. So, first off, we are taking attendance. We talked about that a week ago. Attendance will be a small part of your grade, and it's reasonably lenient. It allows you, I think, maybe 3 absences or something without any penalty. So, what's the point? Hopefully it'll be really helpful. I'm going to encourage you, under the guidance of a grad student TA. The names are either Ben or Reese, depending on which section you're in. They will, for about half of each recitation, and then these are short, they're only 15 or 55 minutes maybe. For about half of the recitation, they're going to divide you up into maybe groups of 2 or 3. And just in small groups, you guys are going to work through 1 or at most 2 problems in recitation each week, obviously on the relevant material. That is an encouragement to have you work in small groups throughout the course in many venues. So hopefully recitations will kind of kick that off in a good way. And then the remaining half of the session, we'll see how this goes, and it'll be up to the TA. We'll be addressing, of course, homework-related questions. Okay? So the reason they're scheduled Tuesday, Wednesday, with homeworks typically due late Thursday, is because hopefully at that point you've been grappling with the homework problems, and you can bring up any homework-related questions in recitation. Okay? So you know I'm very much a supporter of this sort of more active style of learning, and this is one of the ways to really encourage you to get involved in that. A couple of quick things. Hopefully some of you will be interested in one or both the following two groups. SPS, Society of Physics Students. Doesn't mean just physics majors, anyone who's interested in physics or just hanging out with geeky, nerdy people. Not everyone. They meet weekly on Thursdays from 7 till 8 p.m. I'm still trying to figure out where that will meet. And so there'll probably be an email going out sort of blasted broadly across intro physics courses. What's the point of SPS? Good chance to meet with other physics interested students. There's always pizza and soda, talks, just things that maybe of interest to people who are interested in physics. There are students presenting on work they're doing. Oftentimes there'll be faculty coming, so for some of you who are interested in getting involved in physics research, this may be a venue to sort of start meeting faculty and find out how to go about that, and a bunch of other things. So it's kind of an informal, relaxed thing. Even if you don't go on a regular basis, they'll have a mailing list to keep you updated about things that are going on. CSWP, Columbia Society for Women in Physics. Again, meets on Thursdays, this time from 6 until 7, so you can in principle go to both. In that case, there's actually a flyer down here for those of you who may be interested just to pick up on the way out. But they are meeting this Thursday for the first time in the Center for Theoretical Physics, which is up on the 8th floor in this building. So both worthwhile organizations. If you're interested, go along. If you can't make it this week, plan for going in a future week. And just sort of get more involved with students who have interests, hopefully aligned with your own. Okay, last thing. So I tried video in class last Thursday. Seemed reasonable quality. I haven't figured out how to upload it to YouTube yet, but I hopefully will. So I am recording again today, and presumably will continue recording for the rest of the semester. Okay? So once I've figured out how to make it available, that will be a resource. Quality is not great, as you might imagine, with a camera that is 30 feet away and probably doesn't have a particularly high quality microphone, but maybe it's better than nothing. Okay? So just be aware that we are videoing from here on. Okay, questions, comments on anything before we jump into 1D motion? Yes?
So again, for the problem sets, like, are those on a weekly basis?
Yes.
Okay.
Yep. And unless something convinces me to change, they'll usually be due late on Thursdays. What I'll probably do in a week or so, once we've settled into a routine, is ask you guys for general feedback about the course, what's working, what could be done differently. And if I get any sort of clear messages at that point, I will obviously try and respond to them. And for example, homework due date might be one of them. But for now, yes, weekly due Thursday night. Other questions? Yeah. Yeah, yeah. It's a kind of complicated scoring system, as you know. It also has this, what do they call it? Kind of, I don't think, well, there's a bonus, but then there's the add-on bit if you get below a certain threshold. I can't remember what it's called. Anyway, it's adaptive in some way. So I think, roughly speaking, the total score each week must be about 60, because it's 50 assigned with 10 problems, 5 points each. And then this additional add-on, which you get automatically if you get above the threshold, which is like 90 or 95%. And if you need to go back and work a couple of problems, you'll presumably get it as you work through those additional problems. So I think it's 50 plus 10, 60. But then there's this weird scoring aspect of you can get bonuses and things like this. So having looked at some of your scores already in Mastering Physics, on one of the problems, the average score is like 102% or something. So it's a little bit complicated, but of course it's applied the same for everyone. And of course it's the same throughout the semester, so it should be equitable, if not fully transparent.
Are
Yes.
the adaptive problems required?
Yes. Yeah. So again, what's the purpose? If you get beyond a certain threshold, and I thought long and hard about these various thresholds and bonus points and penalties over the weekend, just based on experience of colleagues and prior people who use this system. So I put quite a bit of thought into setting the parameters for it. The motivation for that is it's intended to be an incentive-driven setup, okay? So as I said last week, I in no sense want to penalize you for no good reason. But as I learned a little bit having used this system before, and again from colleagues, if you have no penalty for unlimited attempts at a problem, it actually removes any incentive to think about it and actually figure out what you're doing, because you just keep hitting enter until it gets presumably a right answer. So that's the reason it's set up the way it is. And to come back to your question, are you required to do it? Yes. So if you get beyond the threshold in the original 10 problems, you get those points for free. If you don't, you have to work a little bit harder, but again, you get the points. Okay, other questions? I also noted in reading carefully through guidance on this over the weekend that it said the first time people use Mastering Physics, only about 20% of people told in a class like it. That sounds like a bad advertising thing. But it says by the time you're getting towards the end of the semester, some crazy number like 97% of students using this system think it's both good and helpful. Okay? So there may be a little bit of a learning curve, a little bit of growing pains, so to speak. That's normal. Bear with it. I'm a convinced convert at this point. I think these systems can help, and they can help you really master stuff along the way in a way that is incentive-driven rather than using a stick in some way. So I think you'll find it useful. Okay, let's get into class. So I'm going to start moving a little bit faster now since the first week was a little bit slow. So we're talking about one-dimensional kinematics, and all of you have, I don't know why this thing likes to come on for no good reason. Okay, all of you have a decent calculus background, so I'm going to assume that one-dimensional kinematics. Kinematics, motion, descriptions of motion, how things move, not why they move, not yet. So one dimension, we're going to stick in a line, obviously. That's pretty restrictive as we get started, but if we can master things in a line, it's a fairly straightforward extension to go beyond the line to working in 2 and 3 dimensions. So we need to get one-dimensional motion down first. And to begin this, we need to make sure we've got basics again. We need to understand what we mean by a coordinate system. So I think I will just simply outline this, but if I asked you to come up with a system to unambiguously, let's say, describe where something is, if you think hard about it, you would need at least 3 things. You would need this is in 1 dimension, you would need a defined axis, direction in particular. You would need some reference point or origin, and you would need some sort of scale on which to define, let's say, positions. Okay? So we need these 3 things. Defined axis, we're going to use pretty much throughout, at least in the first semester, probably true in the second semester, a Cartesian axis system, coordinate system, x, y, z, perpendicular coordinate system in 3 dimensions. So we're going to use that very often. And as a convention, we're going to follow what almost all of you have seen most commonly as a convention, which is x being most commonly along the horizontal direction, y most commonly in the vertical direction, and z in the direction that's perpendicular to both of those, namely into or out of the plane of x and y. That's a convention. We're not always going to do that. You can choose which you decide to be x, y, and z, but more often than not, we're going to choose this as horizontal, vertical, and let me call this in and out. But again, that's a convention, okay? And I will try and stress this idea of conventions not being sort of written in stone. We can choose what we like as it suits our convenience. That will be a common convention. Origin, we need to set a 0 point, a reference point, up to us, where we set it. So again, it's a convention, or not even a convention, it's a personal choice, I guess I will describe it as. Now again, you're probably used to some very common choices of origin coordinates. In particular, when we talk about motion vertically, we're very often using, for example, the surface of the Earth as a chosen origin or reference point. So we might define that as y equals 0. But it's our choice, it's the convenience, okay? And then a scale, this obviously means we need to use some specific units. If we're talking about distance, it might be meters in our SI system, but of course it can be anything else. So those are the three things that we need. So, for example, let's talk about motions in the x direction. In principle, the x-axis runs all the way to the right and all the way to the left. It's infinite. I'm going to set x equals 0 randomly at this point. And then I'm going to define positions relative to this origin simply by saying where they are on this scale. So this might be a point which is x equals, I don't know, plus 1.5 meters, something like this. Okay, so now we've got all the three ingredients. Okay, it's important for me to note that when we're talking about things that have directional information, which implicitly or even explicitly they do in an axis, these are vector quantities. So all of the quantities we're going to talk about in one-dimensional motion, more or less, are vector quantities. So let me talk a little bit about notation. I've already started, just lower this one notch because it's almost wanting to give some feedback. Okay, so we need to talk about notation. Very often we'll talk about positions, position vectors, the usual notation, an arrow above the relevant variable, so I'm going to use that throughout the course. And I will just mention at this point, which hopefully you guys looked at over the weekend, because I asked you to study unit vectors. For those of you who haven't seen it before, it's kind of important for everyone. We'll use them once in a while. What is the role of a unit vector? Well, a vector carries both size and directional information. Keep that in mind always. Two things, size and direction. So I can break those two things apart. And for example, in this case, I might put the size information like this, plus 1.5 meters. Or in fact, maybe I want to write that slightly differently, plus 1.5 meters. That's the size information. There's kind of a bit of directional information in here, which is why I decided to pull it out. And then what I could use is this, the I hat unit vector. So this is a vector which is only a sort of semi-vector in the sense that it only contains directional information. It has no size information. So I'm ignoring size information and just saying that this is a unit vector pointing along the direction which happens to be the x-axis. And again, you should have read this over the weekend. There are unit vectors j hat and k hat that correspond to directional information only along the y and z axes respectively. Okay? So this would be a possibly slightly unusual way, but certainly valid way of writing x. Here's the magnitude information. Here's the directional information. And this plus also carries some directional information, right? Because it's telling us it's in the plus direction. If I happen to have something over here, same distance away, of course, that would be minus. So the minus or the sign here can be combined with the unit vector truly carries the directional information. Okay? Right. So now we've got a coordinate system, we've defined vectors. Let's start talking about physical quantities. We've already been introducing one. It's kind of position. And I really don't have anything more to say about this. We've already defined everything we need to know where something is. And so this would be defining a position of some object for us at some point. Okay? So some point in time. So pretty much we've already done this. What I may care about, however, next is if something changes its position. This is what we tend to call a displacement. I'm not going to write up change of position because I think all of you are familiar with this. And we might, for example, write it as something like that. Delta x, this is the standard symbol in math and physics, capital delta for a change in something. So a change in x position, we will define as being the position at some later time or later measurement, 2, the second, minus the position at some earlier time or initial time, 1, the first, okay? x2 minus x1. So this would be a measure of change of position. We haven't yet introduced time, but we're about to. Let me just say, as I kind of start going along through this, it's a little bit of an aside, but it's kind of a good time to mention it. We're often, as we talked about last week, dealing with idealization. And for us, for the next little while, we're going to treat objects which are usually large, macroscopic, extended. We're going to treat them as points. So that's an idealization. The assumption somehow is that for an extended object, all parts of that object are moving in a common way. And if that's the case, we can, in many instances, as we get started in mechanics, assume that the object can be treated simply as a point, and all points on the actual object move in sync with that point that we're choosing as a reference. Quite why we can do that, we'll only come to later in the course, but for now, if you'll accept it, it makes our life a lot easier. Okay, so now we've got positions and displacements. As I said, we haven't yet explicitly introduced time, but now let's go ahead and do it. So, time. Try and keep some consistency in chalkboard use here. Time, variable, little t. Okay, standard units, SI units, seconds, but it could be other things. So time obviously factors into motions. Things are in different places at different times, so it's important that we take account of time. What we will often worry about is not just a measurement at a particular time, but a time interval, which I'll often call the elapsed time between one event and the second event. So we might describe this as a difference in time or a change in time. And as we had on the left-hand board for position, we may simply define that elapsed time or change time as t2 minus t1. First event, second event, okay? Consistent notation. So this very quickly leads us to the idea that combines both of these quantities, position and time. And I'm going to define velocity, okay? So, pretty much in line with your day-to-day use of the word velocity, it's a measure of change in position over some certain elapsed time interval. Let me write it down as an expression, a definition even, and then see if that ties in with your intuition. Hopefully it does. I'm going to write something here which there are two kind of sub-comments associated with. So first off, v, little v, I'm going to define as delta x over delta t. And let me write this out fully, just as we get going. Most of you have seen these sorts of things before. And even those of you who haven't, I'm imagining sort of a reasonably logical progression. So I'm going to define the velocity as displacement over elapsed time. Okay, so I said I was going to make two sub-comments about this. First off, this is a vector. I didn't explicitly mention this, but t is not a vector because it doesn't have any directional information it carries. It's what we call a scalar quantity. So it only has magnitude, it doesn't have directional information. So I've got a vector quantity that I'm dividing by a scalar quantity. What does that tell me this needs to be? By which I mean, is it scalar or is it a vector? Vector. Good. So anything that is built up of something that carries directional information must itself carry directional information. With a few caveats. Let's say that's true. So good, it's a vector. has directional information associated with it. The second thing I want to say about this is how might we represent this visually, and then what does that tell us specifically about this V parameter. So I'm going to, for the first time, draw a kind of two-dimensional plot, and it may be a plot of position versus time. And let me draw some random motion on here. Do I really want to draw some random motion? Maybe not. I'm going to draw some slightly non-random motion. I'm going to draw that. Okay. So let's take a look at this. This is a representation of the position in x of some object as a function of time. We're going to start talking about functions quite a bit in a little while. Somehow it starts off here at time t1, apparently ends up here at time t2. Apparently when it started off it was at a position x1, and when it ended up it's at a position x2. So there's a nice, obviously, correspondence between this formula and this graph plot, namely that delta x is this, and delta t is this. All right, so visually, when I say that this velocity is defined as delta x over delta t, what does that correspond to on a plot like this? Slope, yeah. So the slope is indeed delta x over delta t. I've forgotten the vector arrow here, it doesn't matter, this is a plot rather than a kind of vector representation. So the slope of something like this represents the velocity of an object. Good. All right, so here I have something that has a positive slope, and it seems to be a straight line. So if this is a straight line, what does it tell you about this thing that we've just defined as being the velocity? It's constant, right? Excellent. So I've already got from a graphical representation of this some interesting information. The sign of the slope will tell us whether it's a positive or a negative velocity. If this thing was horizontal, what would you tell me about the velocity? Zero. Good. Okay. All right. So in fact, what I'm doing here is defining rise over run, or the slope of this thing between that point and that point. Now, it's entirely possible, rather than have something that moves like that, I would have something that moves like that. Same beginning, same end point. If I define V as delta x over delta t, as I've defined it here, is V, as it's defined so far, is it the same for this red curve as the green curve, or is it different? It's the same, right? So in fact, what we're leading towards here is the idea that this V is in fact an average velocity over that time interval. So that's important. It's an average over a given time interval. But if we had motion that was like this red one, life's not so simple. And in fact, the velocity, which is always given by the slope of this curve, in the case of the red one, is continually changing, or more or less continually changing. And that might be something else that we're interested in, namely not the average velocity over this elapsed time interval, but the instantaneous velocity anywhere. Okay? So, with that in mind, I'm going to define now the instantaneous velocity as average, now instantaneous. And I'm hoping this is absolutely familiar to everyone in the class. The way I'm going to define this initially is to take my time interval, delta t, and make it really, really small. So I'm going to take this time interval and shrink it and shrink it and shrink it. As I do so, presumably I'm figuring out or approaching the slope at any particular point, so the near instantaneous velocity. And of course, what this is actually doing is telling us that we need this to be the instantaneous derivative of position with respect to time dx by dt. Okay? So we're going to use this standard differential notation and definition of the instantaneous velocity.